When you write code, you usually think about logic, functions, loops, algorithms, but in modern processors, performance is often determined by something much more fundamental: how fast the CPU can access memory. And that's where caches come in. In this video, we're going to explain what CPU caches are, why they exist, how they work at a high level, what L1, L2, and L3 mean, and why memory hierarchy is one of the most important concepts in software execution. Let's begin with the core problem. CPUs are extremely fast. Modern processors can execute billions of instructions per second, but main memory, RAM, is much slower compared to the CPU's internal speed. If the CPU had to wait for RAM every time it needed data, performance would collapse. The processor would spend most of its time idle. This mismatch between CPU speed and memory speed is called the memory wall. Caches exist to reduce that gap. A cache is a small, fast memory located very close to the CPU core. Instead of accessing RAM directly every time, the CPU first checks whether the data it needs is already in the cache. If it is, the access is much faster. If it's not, the processor must fetch it from the next level of memory. This leads to the idea of a memory hierarchy. Rather than one type of memory, modern systems have layers. Registers are the fastest and smallest. Then comes L1 cache, then L2 cache, then L3 cache, then main memory, then storage. As you move down the hierarchy, memory becomes larger but slower. The goal of the cache system is simple: keep frequently used data close to the CPU. Now let's talk about why this works. Most programs exhibit something called locality. There are two main types. Temporal locality means that if you access a piece of data, you're likely to access it again soon. Spatial locality means that if you access one memory address, you're likely to access nearby addresses soon. Caches are designed around these principles. When the CPU fetches data from memory, it doesn't just load a single byte. It loads a block of memory called a cache line. A typical cache line might be 64 bytes. That means when you access one value, the CPU also loads nearby values into the cache. This exploits spatial locality. If your program accesses memory sequentially, like iterating through an array, caches work extremely well. Now let's discuss cache levels. L1 cache is the smallest and fastest. It is located directly inside the CPU core. There are often two L1 caches, one for instructions, one for data. This allows the processor to fetch instructions and data simultaneously. L2 cache is larger, but slightly slower. It still sits close to the core. L3 cache is larger still and often shared across multiple cores. Each level acts as a backup for the one above it. If data isn't found in L1, the CPU checks L2. If it's not in L2, it checks L3. If it's not in L3, it must fetch from RAM. This process is called a cache lookup. If the data is found, it's called a cache hit. If it's not found, it's a cache miss. Cache hits are fast, cache misses are expensive. Now, let's explore why misses are costly. If the CPU must fetch data from RAM, it may take hundreds of clock cycles. During that time, execution units may stall if they depend on that data. Even with out-of-order execution, if there is not enough independent work available, performance drops. This is why memory access patterns matter so much. Now let's talk about cache organization. Caches are not just simple storage, they are structured into sets and lines. When data is placed in the cache, it must be stored in a specific location based on its memory address. This mapping process determines where data can reside in the cache. Different cache designs use different mapping strategies. Some use direct mapping, where each memory block has exactly one possible location. Others use set associative mapping, where each block can go into one of several possible locations within a set. Higher associativity reduces the chance that useful data will be evicted unnecessarily. Eviction happens when the cache is full and new data needs to be loaded. The processor must choose which existing cache line to replace. Common replacement strategies try to remove data that hasn't been used recently. Now let's connect caches to performance engineering. If your program accesses memory in predictable sequential patterns, caches are very effective. If your program jumps around randomly in memory, cache performance suffers. For example, iterating through an array linearly is cache-friendly. Accessing elements scattered across memory with large gaps is cache-unfriendly. This is why data layout matters. Sometimes restructuring data can dramatically improve performance without changing the algorithm. Now let's discuss instruction cache versus data cache. The instruction cache stores program instructions. The data cache stores variables and memory values. If your program has tight loops, the instructions for that loop will likely remain in the instruction cache. This makes repeated execution fast. But if your program jumps frequently between distant code sections, instruction cache misses may increase. Now let's introduce another concept: cache coherence. In multi-core systems, each core has its own cache, but they all share main memory. If one core modifies a value, other cores must see that change. Cache coherence protocols ensure that cached copies remain consistent across cores. This adds complexity, but is essential for correctness in parallel programs. Now let's connect caches to SIMD and superscalar execution. Superscalar architecture allows multiple instructions per cycle. SIMD allows multiple data elements per instruction, but both increase demand for data. If the cache cannot supply data quickly enough, execution units will stall. Wide execution without efficient caching is useless. This is why memory hierarchy is just as important as execution units. Now let's address a common misconception. Some people think cache size alone determines performance, but size is only part of the story. Latency matters, bandwidth matters, associativity matters, replacement policy matters, and most importantly, how your program accesses memory matters. Now let's zoom out. In the execution model we've built so far, instruction dispatch selects what to run. Branch prediction keeps control flow smooth. Pipelines overlap execution. Out-of-order execution reorders work. Superscalar issues multiple instructions per cycle. SIMD processes multiple data elements per instruction. And caches ensure data arrives fast enough to keep everything moving. Without caches, modern CPU performance would collapse under memory latency. Caches are the bridge between ultra-fast processors and comparatively slow main memory. They make high-performance computing possible. At a deeper level, understanding caches helps you understand why some programs are fast and others are slow, why certain data structures perform better, why memory access patterns dominate performance in many workloads, and why optimizing algorithms sometimes means optimizing data layout, not just computation. If you want to continue deeper, the next step could be exploring memory latency and bandwidth in more detail, or diving into cache coherence and multi-core behavior. But for now, you can summarize CPU caches like this. CPU caches are small, fast memory layers that store frequently accessed data close to the processor, reducing the performance penalty of accessing main memory. And they are one of the most critical components of modern software execution.